The invisible rays of radar became one of the decisive factors of World War II. As aerial warfare on an unprecedented scale unfolded in the skies over Europe, the ability to detect approaching enemy aircraft became a matter of survival for entire cities and military installations. By 1943, a genuine technological race for superiority in radar technologies had flared up between the warring powers. Germany, which had invested enormous resources in developing this field even before the war began, created an entire network of radar stations covering occupied Europe and the Third Reich itself. The Soviet Union, despite having its own developments, significantly lagged behind the Germans in the practical application and accuracy of radar equipment. While German radars could detect aircraft at distances of hundreds of kilometers and guide anti-aircraft artillery with astonishing precision, Soviet installations often malfunctioned and had a limited range. It became evident to the military leadership of the USSR. Without a breakthrough in this area, it would be impossible to ensure reliable protection of strategic facilities and achieve air superiority. Among all German radar systems of World War II, the Würzburg occupies a special place. This compact but extremely effective station became a true technological breakthrough and transformed into the electronic eyes of the Third Reich's night sky. Created in 1940 by the talented engineer Hans Hollmann, it received its name in honor of an ancient German city and quickly proved its exceptional value to the Luftwaffe. Outwardly, the quote looked quite simple: a parabolic antenna 3 meters in diameter mounted on a mobile platform. But behind this seeming symbolizing lay advanced electronics. The radar operated at a frequency of 560 megahertz, which was a technological marvel for its time. The detection range reached 70 kilometers, and the accuracy of target coordinate determination was several hundred meters, an incredible indicator for the early 1940s. A distinctive feature of the quote was its ability to operate in any weather conditions and in complete darkness. German operators could track British bombers long before they reached their targets. Moreover, the quote allowed not only to determine the direction and range to the target, but also its altitude, which provided a critical advantage in guiding anti-aircraft artillery and night fighters. In Germany's air defense system, the Würzburg usually worked in tandem with the long-range Freie radar, which first detected approaching aircraft at a distance of up to 200 kilometers. Then, the Würzburg would track the target and transmit precise coordinates to anti-aircraft batteries or nearby night fighter airfields. By 1943, the Germans had deployed over 500 such radars along the coast of occupied Europe and within Germany itself. This network became a real nightmare for Allied aviation. British and American bombers suffered heavy losses as German fighters, guided by Würzburgs, attacked them in the night sky with astonishing accuracy. It is not surprising that capturing and studying this technology became a priority for the Allies. Whoever gained access to the secrets of the Würzburg could not only develop effective countermeasures, but also utilize advanced German technologies to create their own new-generation radar systems. On the night of February 27th to 28th, 1942, on the rocky coast of France, near the town of Bruneval, British commandos carried out one of the war's most audacious operations, Operation Biting. Its goal was to capture the German, quote, radar, installed on a high cliff and guarded by a Wehrmacht garrison. The idea for the operation belonged to the British scientist Reginald Jones, who, analyzing aerial photographs, noticed strange structures on the French coast. It was he who convinced the command of the necessity of capturing the radar intact rather than simply destroying it. To accomplish this task, a special group of 120 commandos was formed under the command of Lieutenant Colonel John Frost. Preparation was thorough. Soldiers trained on a mock-up of the radar station, studied its design, and practiced the procedure for dismantling key components. British scientists compiled detailed instructions, which parts of the radar were most valuable and how to quickly remove them. A landing craft delivered the commandos to the French coast after midnight. The soldiers in inflatable boats covered the last meters to the beach and began ascending the steep slope. A covering group blocked approaches to the radar station while technical specialists began their work. Despite the ensuing battle with the German garrison, the British methodically dismantled key elements of the, quote, waveguides, magnetron, antenna elements, control units. In just 10 minutes, they collected invaluable components and began their withdrawal to the shore. The operation was completed in less than 2 hours, and the commandos returned to England with minimal losses. The captured radar parts were immediately delivered to a research center in Malvern, where the best British scientists began studying them. The results exceeded all expectations. The British gained a full understanding of the principles of the German radar's operation, the frequencies used, and the technical solutions. Particularly valuable were the receiver and transmitter elements, which allowed them to understand how the Germans achieved such high accuracy. The knowledge gained was of colossal importance. Firstly, the British developed effective electronic countermeasures, the famous window foil strips, also known as dipole reflectors, which created many false targets on German radar screens. Secondly, the technological solutions of the Würzburg were used to improve their own radar systems. The success of Operation Biting did not go unnoticed by the Allies. Information about the captured technology was transmitted to the Americans and Soviet representatives. This operation clearly demonstrated that gaining access to advanced German radio technologies was not just a desirable, but a critically necessary task for all countries of the anti-Hitler coalition. The British experience became a valuable lesson and example for Soviet intelligence, which soon began planning its own operation to capture German radar equipment. By the start of the war, the Soviet Union had serious developments in radar technology, but reality proved harsh. The first Soviet radars of the RUS series, aircraft radio catchers, although created back in the 1930s, were significantly inferior to their German counterparts in accuracy, reliability, and detection range. The RUS-2 station could detect an aircraft at a distance of up to 100 kilometers, but with an error of up to 8 kilometers in range and up to 4 degrees in azimuth, an inadmissible luxury for precise targeting of fighters or anti-aircraft artillery. German raids on Soviet cities revealed critical shortcomings in domestic radar technology, while Würzburgs allowed the Luftwaffe to conduct pinpoint bombings even in zero visibility conditions. Soviet anti-aircraft gunners often operated blindly, relying on sound locators and searchlights. The problem was especially acute during the defense of Moscow and Leningrad, when German aviation struck in difficult weather conditions. Why did such a lag occur? There were several reasons. Pre-war repressions affected many talented radio engineers. Industry failed to establish mass production of radar equipment before the war began. There was a sharp shortage of components, special lamps, capacitors, high-frequency cables. But most importantly, there was a lack of understanding of the strategic importance of radar at the highest level of government leadership. Everything changed after the heavy losses of the first years of the war. In 1942, the State Defense Committee issued a special decree on the development of radar. New research institutes, laboratories, and design bureaus were established. Production lines were deployed in factories evacuated to Siberia and the Urals. By the middle of the war, more advanced stations of the Pegmatit and Redoute series appeared, but they still lagged behind German models in key parameters. Soviet designers understood a technological breakthrough was necessary, and it could only be achieved by gaining access to advanced German developments. The Kremlin carefully studied the experience of the British Boadicea operation and concluded that the USSR needed to conduct a similar operation. The General Staff and the NKVD understood. Capturing a working Würzburg would save years of research and thousands of lives of Soviet soldiers and civilians. Of particular value were the circuit design solutions of German engineers, which allowed for high measurement accuracy, as well as the technology for manufacturing magnetrons, the heart of the radar system. Soviet industry faced enormous difficulties precisely with the production of these components. In early 1943, Soviet intelligence began collecting information about the location of German radar stations near the front line. The task was to find a position that was close enough to Soviet positions, but at the same time had a complete and preferably the latest model of Würzburg. The task seemed almost impossible, but too much depended on its solution. The operation to capture the German Würzburg radar began not with loud orders and large-scale actions, but with painstaking intelligence work. In the spring of 1943, the main intelligence directorate formed a special group of analysts, which included not only experienced intelligence officers, but also radio engineers capable of assessing the technical value of potential trophies. The first step was to collect fragmented data on the deployment of German radar stations. Partisan detachments operating behind enemy lines were tasked with recording unusual structures with parabolic antennas. Reconnaissance pilots, returning from missions, reported on spotted radar installations. Intercepted German communications also provided valuable clues about the location of air defense facilities. Gradually, on the map of the western regions of the USSR occupied by the Germans, marks of possible radar posts appeared. By the summer of 1943, analysts had identified several most promising targets located near the front line. The key selection criterion was not only the accessibility of the object, but also the probability of finding the latest modification of the Würzburg there. Particular attention was drawn to a radar station discovered by Captain Ivan Shilov's reconnaissance group in the area of a small settlement 20 kilometers from the front line. According to reports, the Germans had installed the latest Würzburg Riese there, an improved version of the radar with increased range and improved accuracy. A special group was sent for detailed reconnaissance of the object, which included radio engineer Lieutenant Boris Meshcheryakov. Dressed in civilian clothes, the scouts observed the station's work for several days, recording the location of guard posts, changes of guard, and technical personnel. Meshcheryakov, using a special device, confirmed that the station was emitting at a frequency characteristic of the Würzburg. The obtained data allowed for a detailed plan to be drawn up. Night was chosen as the optimal time for the operation, when visibility is limited, but the radar continues to operate. The assault group was to consist of 15 people, 10 fighters to neutralize the guard and provide cover, 5 technical specialists to dismantle key components of the radar. A particular difficulty was the issue of transporting the captured equipment. Engineers prepared special containers for the most valuable components: the magnetron, waveguides, control units, and indicator devices. The weight of the entire set was about 100 kilograms, a difficult burden for the return journey across the front line. In case it was impossible to evacuate all the equipment, a list of priorities was drawn up. which parts of the radar were of the greatest value. Engineers prepared detailed instructions for quick dismantling, numbering each element and indicating the sequence of actions. To ensure the successful withdrawal of the group, a complex scheme with feints and adapting actions was developed. On the night of the operation, it was planned to organize an artillery bombardment on an adjacent sector of the front to distract the attention of the German command. On the night of July 5, 1943, a group of Soviet scouts commanded by Major Alexei Kovalev prepared to execute one of the war's most audacious operations. 15 fighters, carefully selected from among the best scouts and technical specialists, gathered in a small forest 3 kilometers from a German radar station. Their faces were smeared with soot, and their weapons were wrapped in rags to prevent any accidental metallic clinking. Kovalev quietly commanded. Engineer Captain Sergei Danilov double-checked the contents of a special backpack containing tools for dismantling. Inside were screwdrivers, wire cutters, special wrenches, and diagrams with numbered components of the drag. The group moved through the forest silently, like shadows. Intelligence reported that the radar was guarded by 8 German soldiers and 3 technicians on rotating shifts. A key part of the plan was to neutralize the guards without a single shot. Any alarm could lead to the destruction of the equipment. At 2330 hours, when the group was half a kilometer from their target, Soviet aircraft appeared in the sky. This was a diversionary maneuver. Several bombers simulated an attack on positions 10 kilometers from the radar station. The Germans, as expected, activated the radar to track the aerial targets. The scouts seized the moment. 4 fighters silently neutralized the sentries on the outer perimeter. The main group penetrated the station's territory. The radio technicians were disarmed with a sudden strike. One German soldier attempted to raise the alarm, but Senior Sergeant Nikolai Petrov swiftly overtook him with a lightning-fast lunge and silenced him. "We have 20 minutes, no more," Kovalev commanded, looking at his watch. The engineers immediately began their work. Danilov directed the dismantling process, clearly indicating which components to remove first. First the magnetron and waveguides, then the control units and indicators. "Don't damage the contacts," he instructed his assistants. The work proceeded quickly and methodically. Each part was carefully packed into pre-prepared containers with soft padding inside. Suddenly, voices were heard from the German dugout. It was the changing of the guard, arriving earlier than scheduled. Lieutenant Igor Sokolov and 3 fighters immediately took up covering positions, ready to engage if necessary. Fortunately, the German soldiers, seeing activity at the station and silhouettes in German uniforms, the scouts were dressed in captured uniforms, did not suspect anything amiss. They assumed the technicians were conducting unscheduled maintenance due to the air raid. After 17 minutes, the key components of the radar were dismantled. "Let's go!" Kovalev commanded. The group began their retreat, moving along a pre-scouted route. The heavy containers with equipment were carried, with group members alternating every 500 meters. Crossing the front line was the most dangerous stage. The group reached a small river where an inflatable boat awaited them. 4 fighters crossed first, securing a bridgehead on the opposite bank. Then the equipment was transported, and finally, the rest of the group. On the Soviet side, a truck with reinforced security was already waiting for the scouts. The valuable cargo was immediately delivered to the front headquarters, and from there, flown to Moscow, where the best Soviet radio engineers eagerly awaited it. The priceless trophy arrived in Moscow late at night. A special plane landed at a military airfield, where a group of leading Soviet radio engineers was already waiting for the captured Würzburg. The radar components were carefully packed in wooden crates with felt lining, protecting the fragile electronics from jolting during transport. Each part was numbered and accompanied by detailed layout diagrams drawn by Captain Danilov right during the operation. When the crates were opened in the spacious hangar, a reverent silence fell. Before the Soviet scientists lay something that could change the course of the air war. Professor Alexander Mintz, who led the research group, was the first to break the silence. From this moment, a new chapter in the history of our radio location begins. The very next day, specialists at the secret NII Scientific Research Institute near Moscow began a methodical study of the German technology. Work continued around the clock, in 3 shifts. First, the captured components were carefully laid out on long laboratory tables, recreating the radar's original configuration. Engineers sketched diagrams, photographed every detail, and compiled detailed descriptions. Particular attention was drawn to the magnetron, the heart of the radar station. The German sample had several fundamental differences from Soviet counterparts. Its resonance system was made with astonishing precision, ensuring the stability of the emitted frequency even when the ambient temperature changed. Young radiophysicist Yuri Korovin, who was studying the magnetron, did not hide his admiration. "Look at this metalwork. The tolerances do not exceed 20 microns. Our factories cannot yet provide such precision." The Würzburg antenna system also aroused professional interest. German engineers used a special parabolic reflector shape and an original feed horn design, which ensured the formation of a narrow directional beam with minimal side lobes. This made it possible to accurately determine the direction to the target, even in the presence of interference. In parallel with the study of the hardware, work was underway on the software component. The Würzburg indicator devices used original signal processing schemes that allowed filtering out noise and extracting the useful signal even with a weak reflection from the target. Soviet specialists meticulously documented every technical solution, comparing them with domestic developments. After 2 weeks of continuous work, the first preliminary report for the State Defense Committee was prepared. It highlighted the key advantages of the German system and proposed ways to implement the captured technologies in Soviet radars. In parallel with the laboratory research, work began on recreating a working prototype. Using both captured parts and domestic components, engineers assembled a hybrid system that allowed for full-scale field testing. The experiments confirmed the high effectiveness of the German technical solutions. Particularly impressive was the accuracy of determining the coordinates of air targets, several times higher than that of Soviet stations of that time. When Soviet engineers completed their initial study of the captured Würzburg, the analysis results exceeded all expectations. The German radar proved to be a true technological gem, embodying a host of innovative solutions unavailable to Soviet radar technology at the time. First and foremost, specialists were struck by the antenna system. German engineers created a parabolic reflector of special geometry that formed an exceptionally narrow beam, just 1.5 degrees in the horizontal plane. For comparison, Soviet RUS-2 radars produced a beam approximately 10 degrees wide. This difference fundamentally affected the accuracy of target coordinate determination. Professor Shchukin, who led the technical analysis, noted in his report, "Thanks to such beam focusing, the Germans gain a 10-fold advantage in accuracy compared to our stations." The second revelation was the transceiver system. The Würzburg used a duplex operating method with a special switching device, an antenna commutator. This allowed a single antenna to be used for both transmitting and receiving signals, which significantly simplified the design and increased accuracy. Soviet stations of that time operated on a separate scheme, requiring 2 antennas and a complex synchronization system. The Würzburg's display system caused particular admiration. German designers developed an original type of indicator, the so-called circular scan indicator. On the round screen of the cathode ray tube, the operator saw not just signal spikes, but precise target marks linked to coordinates. This method of displaying information greatly simplified operator work and increased reaction speed to air threats. Engineer Colonel Lobanov, who studied the indicator system, wrote, "The German operator sees the air situation clearly, as if on the palm of his hand, while our specialists are flowering to decipher complex oscillograms." No less important was the discovery of the automatic target tracking system. The Würzburg used the principle of conical scanning. The antenna made small circular movements, creating a conical beam. When the target deviated from the antenna axis, a characteristic modulation of the reflected signal occurred, which was processed by special circuits that issued commands to the antenna drives. This allowed the antenna to be automatically kept directed precisely at the target without constant operator intervention. The component base of the German radar also proved astonishing. Magnetrons, klystrons, and other electro-vacuum devices were manufactured with incredible precision. Ceramic insulators with metallization were particularly impressive, a technology that Soviet industry did not yet possess. These components ensured stable operation of the transmitter at high frequencies, even under extreme temperatures and vibrations. Analysis of the circuit solutions revealed an original interference suppression system. German engineers developed multi-stage signal filtering, allowing the isolation of reflections from aircraft against the background of natural interference, rain, snow, clouds. Such filters significantly increased the radar's effectiveness in difficult weather conditions. The study of the Würzburg allowed Soviet specialists not only to understand the principles of advanced radar technology, but also to identify its vulnerabilities. It became clear that the German radar was sensitive to certain types of electronic interference, especially dipole reflectors, which the Allies had already begun to use. This information was of immense importance for developing countermeasures against German air defense. The study of the captured Würzburg marked a turning point for Soviet radar production. The technological secrets gained immediately began to be implemented in domestic developments. By the autumn of 1943, based on German solutions, the experimental station Pegmatit Würzburg was created, a hybrid combining Soviet component base with German circuit design principles. The first serial radar to embody captured technologies was the Tori station. It used an antenna system similar to the German one, with a parabolic reflector forming a narrow beam. The reflected signal processing system was also built on Würzburg principles, which increased the accuracy of target coordinate determination by 3 to 4 times compared to previous Soviet models. Particularly important was the introduction of the all-around view system. If previously Soviet operators only saw amplitude spikes on the linear sweep of an oscilloscope, now they received a full radar picture of the airspace. Targets were displayed as bright dots against a circular sweep, which radically simplified operators' work and increased the speed of reaction to air threats. In late 1943, production of the JUICE station began, the first fully Soviet radar created with all the technological lessons of Würzburg in mind. This station could detect aircraft at a range of up to 120 kilometers with coordinate determination accuracy up to 500 meters. Figures comparable to German counterparts. One of the key breakthroughs was the mastering of high-frequency ceramic component production. Soviet engineers, having studied German samples, developed a technology for ceramic metallization, which allowed for the creation of reliable waveguides and other microwave elements. The Svetlana factory in besieged Leningrad, despite the most severe conditions, established the production of magnetrons with characteristics close to German ones. The introduction of captured technologies into the troops happened rapidly. By early 1944, the first new generation stations arrived at air defense units covering Moscow and Leningrad. Operators underwent accelerated training to work with the new equipment. Moscow Air Defense veteran Sergeant Nikolai Savelyev recalled, "When we received the new stations, it was like an epiphany. Before, we were like groping for planes in the sky, but now we saw them clearly and distinctly, as if in the palm of our hand." For aviation, specialized airborne radars Gneis 2 were developed, also utilizing German radar principles. These compact stations were installed on night fighters and allowed them to independently detect enemy bombers without ground guidance. Fighter pilot Ivan Kojedub, who mastered an aircraft with radar, said, "With this device, I began to see at night almost as clearly as in the daytime. The Germans lost their advantage in night raids." The implementation of captured radar technologies radically transformed the capabilities of Soviet air defense. By the spring of 1944, the first new generation radars were already on combat duty, protecting key cities and military installations. The effect was astonishing. The detection range of enemy aircraft increased by more than 1.5 times, and the accuracy of coordinate determination grew by 3 to 4 times. Anti-aircraft batteries equipped with the new targeting stations demonstrated striking effectiveness. If previously an average of about 2,000 shells were required to hit one German bomber, now this figure dropped to 400 to 500. The ammunition savings were enormous, but more importantly, the probability of intercepting enemy aircraft radically increased. The modernized air defense system of Moscow showed particularly impressive results. On the night of July 22, 1944, German aviation made its last attempt at a massive raid on the capital. New generation radars detected the approaching bombers at a distance of 110 kilometers, which provided enough time for fighters to scramble and for anti-aircraft artillery to be brought to full combat readiness. The result was devastating for the Luftwaffe. Out of 46 bombers that participated in the raid, 27 were shot down, most of them while still approaching the city. Not a single aircraft broke through to the center of Moscow. The commander of Moscow's air defense, Colonel General Gromykin, noted in his report, "The radar revolution also changed the tactics of fighter aviation. Soviet pilots no longer depended on visual contact with the enemy. Guided from the ground with precise coordinates, they could attack German aircraft even in difficult weather conditions and at night." Hero of the Soviet Union, Vitaly Popkov recalled, "Night fighters equipped with airborne radars, developed based on captured technologies, proved particularly effective. Major Zakutny's squadron, one of the first to receive such aircraft, shot down 32 German bombers in 3 months of fighting, 26 of which were during night sorties." By the autumn of 1944, new radar stations began to arrive in troops on all fronts. Their impact was particularly noticeable during the liberation of the Baltic states, where German aviation actively tried to support its retreating troops. The precise guidance of Soviet fighters and anti-aircraft artillery led to catastrophic Luftwaffe losses, up to 70% of aircraft participating in combat sorties. The German command was forced to admit the loss of its technological advantage. An intercepted radio message from General Richthofen, commander of Aviation Group Ostland, stated, The Russians have somehow improved their detection systems. Our aircraft are intercepted long before reaching their targets. Losses are becoming unacceptable. The capture of the German Würzburg radar not only improved Soviet air defense, but also opened entirely new horizons for aviation. Soviet designers now had access to technologies allowing aircraft to see in all conditions, at night, in fog, under cloud cover. This fundamentally changed the capabilities of bomber and reconnaissance aviation. The first step was the creation of an airborne radar station based on Würzburg technologies. Engineers at NII-8, under the leadership of Alexander Raspletin, developed a compact airborne radar, the Gneiss-5, which could be installed on long-range IL-4 and PE-8 bombers. This device allowed not only the detection of ground targets, but also precise navigation, even in the absence of visible landmarks. Previously, in difficult weather conditions, we flew practically blind, relying only on the navigator's calculations, recalled Lieutenant Colonel Vasily Senko, commander of a bomber regiment. With the advent of radars, we began to see the ground through the clouds, unerringly identifying large cities, rivers, lakes, and railway junctions. The new technology proved especially valuable for night bombings. While previously crews could only orient themselves by characteristic light landmarks or with the help of illumination bombs, the radar now allowed them to precisely hit targets even in absolute darkness. This significantly increased the effectiveness of strikes against enemy objectives. In April 1944, an air regiment equipped with bombers featuring radars conducted an experimental raid on a railway junction in the enemy's rear. Despite continuous cloud cover and nighttime, 80% of the bombs fell within 500 meters of the target, a result previously unattainable even in ideal conditions. Radar technologies also revolutionized aerial reconnaissance. PE-2 reconnaissance aircraft, equipped with modified radars, could detect enemy troop movements at significant distances regardless of the time of day or weather conditions. Tracking railway convoys proved particularly effective. The radar unerringly distinguished them even against a wooded background. Quote, noted Colonel Nikolai Gerasimov, head of the Air Army's Intelligence Department. The enemy could no longer hide their movements under the cover of night or bad weather. No less important was the use of radar for coordinating the actions of large air formations. Special guidance aircraft, equipped with powerful radars, could monitor the air situation within a radius of up to 200 kilometers, guiding bombers and escort fighters along optimal routes. This allowed massive airstrikes involving hundreds of aircraft, even in complex weather conditions. In early 1945, when Soviet aviation supported the offensive in East Prussia, the new technologies underwent their true baptism of fire. Despite the foggy and cloudy weather characteristic of the Baltic, Soviet bombers delivered precise strikes against enemy fortifications and communications. The German command was dismayed. They had expected bad weather to protect them from air raids, as it had before. Radar technologies also changed air combat tactics. Fighters equipped with compact radars could detect the enemy at a distance of up to 8 kilometers even in clouds. This gave a decisive advantage in maneuvering and taking an advantageous position for attack. German aces, accustomed to relying on visual contact and their own skill, increasingly found themselves in a losing position. The capture of Würzburg opened up for Soviet scientists not only new possibilities for defense, but also a fundamentally different way of waging war, electronic warfare. Having gained access to the technological secrets of the German radar, our specialists were able to develop effective countermeasures against enemy radar. This invisible war of frequencies unfolded in the air long before the first bombs fell on their targets. The first step was the creation of special jamming stations, codenamed sirens. Their operating principle was simple and elegant: to generate a powerful noise signal at the operating frequency of German radars. When such interference was superimposed on the reflected signal from an aircraft, Würzburg operators would see only chaotic flashes on their screens instead of clear target marks. Engineer Major Viktor Govorov, who led the development of sirens, recalled, "We created our station in just 2 months. Knowing the exact characteristics of the German radar, we could fine-tune the interference with jewelry-like precision. It was a kind of electronic artillery, invisible, but extremely effective." The first tests of the jamming stations took place in June 1944 near Minsk. A group of PE-2 bombers raided German positions, accompanied by a special aircraft equipped with sirens. The result exceeded all expectations. German anti-aircraft guns opened fire late and fired inaccurately, and enemy fighters were unable to intercept Soviet aircraft. The next step was the creation of passive electronic countermeasures. Soviet specialists, having studied the experience of the British, developed their own dipole reflectors, thin strips of metallized paper dropped from aircraft. The length of these strips was calculated precisely to resonate with the wavelength of German radars. Each such strip created a reflection comparable to that of an entire aircraft. When thousands of such reflectors were released into the air, a huge cloud of false targets appeared on German radar screens. Operators could not determine where the real aircraft were and where were just strips of foil. This tactic was called radar rain and was first used during the raid on Königsberg in April 1945. At the same time, active imitation means were also being developed. Special transmitters, installed on small, unmanned gliders, simulated reflected signals from large bomber formations. German air defense reacted to these false targets, expending ammunition and scrambling fighters, while the real strike was delivered from a completely different direction. The complex application of electronic warfare means proved particularly effective. During the operation to liberate Belarus, the Soviet command developed a multi-layered electronic warfare coverage scheme. First, powerful ground-based jamming stations were activated. Then aircraft scattered dipole reflectors, creating false targets. And finally, special imitation groups used transmitters to create the picture of a massive raid where there was none. The German command was in disarray. Their once impeccable air defense system began to fail. The Luftwaffe suffered heavy losses, and anti-aircraft artillery expended precious ammunition, firing at phantoms. An intercepted report from a German communications officer stated, "The Russians have learned to blind our eyes. We no longer see their aircraft until we hear the sound of engines and the explosions of bombs." Electronic warfare became a new dimension of war. Invisible, but no less important than traditional battles on land and in the air. And in this dimension, Soviet specialists, thanks to the captured Würzburg, were able not only to catch up, but also to surpass German engineers. Technologies captured during wartime often became the foundation for peaceful innovations in the post-war era. The captured Würzburg was no exception. Its influence extended far beyond military applications and laid the groundwork for the development of Soviet science for decades to come. The impact of radar technologies on the establishment of the USSR's atomic industry proved particularly significant. When the war ended in 1945, many engineers and scientists who had been working on adapting captured radars were transferred to a new top-secret project, the creation of the Soviet atomic bomb. At first glance, the connection between radar and nuclear physics seems non-obvious. However, It was precisely the technologies refined through the study of the quote that played a decisive role in creating measuring equipment for the first uranium reactors. Professor Alexander Mintz, who led the research on the captured radar, was summoned by Kurchatov in August 1945. Quote, Mintz later recalled, "It turned out that monitoring processes in a nuclear reactor required neutron and gamma radiation detectors with exceptionally high accuracy. The principles of processing weak signals developed for radar were ideally suited for this task. Amplifier circuits, created based on German designs, were adapted for registering the radiation background inside the reactor. Waveguide technologies proved no less important. They used unique waveguides made of special alloys with ceramic insulators. Soviet engineers not only copied these components but also improved them. These same technologies enabled the creation of cooling systems for the first Soviet reactor F1, launched in December 1946. Radar technologies played a special role in the creation of particle accelerators, an essential tool for studying nuclear reactions. The first Soviet synchrocyclotron, built under the leadership of academician Alekhanov, used high-frequency generators, direct descendants of which were the magnetrons from the captured five. The focusing system for charged particle beams operated on a principle similar to that of a radar antenna's aiming system. Engineer Leonid Vladimirsky, who participated in the creation of this accelerator, noted, "Without experience with radar equipment, we would have spent at least 5 to 6 years developing the accelerator's high-frequency systems. As it was, we managed it in 2 years, using already proven technologies." Another unexpected application of radar technologies was the creation of the first Soviet electronic computing machines. The signal processing systems in the Würzburg used principles close to digital ones. Engineers who worked with captured radars made a significant contribution to the development of the first Soviet electronic computer, MESM, created under the leadership of Sergei Lebedev in 1950. Even in peaceful atomic energy, technologies derived from radar found application. The control and management systems of the world's first nuclear power plant in Obninsk, launched in 1954, largely relied on circuit design solutions refined during the creation of post-war radars. Thus, the captured German Würzburg, seized by Soviet intelligence during the height of the war, became not just a military trophy, but also a catalyst for scientific and technical progress in the post-war USSR. Technologies born for destruction, in the hands of Soviet scientists, transformed into tools of creation, paving the way for peaceful atom and the digital revolution. World War II was not only a clash of armies, but also a battle of technologies. The hunt for advanced German radars turned into a real competition among the Allies. Great Britain, the USA, and the Soviet Union, united against a common enemy, simultaneously competed with each other in the technological race. Each country strived to be the first to obtain the secrets of German radar, understanding their critical importance not only for the ongoing war, but also for the post-war world order. The British proved to be pioneers in this technological hunt. Their Operation Biting in February 1942 became a model for similar actions. A daring commando raid on the French coast yielded invaluable components of the Würzburg, which were immediately studied in research centers. British scientists quickly developed countermeasures, the famous window dipole reflectors, which created numerous false targets on the screens of German operators. The Americans, who entered the war later, actively adopted British experience. However, they took a different path. Instead of risky coastal raids, they focused on capturing entire radar stations during offensives in North Africa and Italy. By 1943, they had several fully functional Würzburgs at their disposal, which allowed them not only to study the technology, but also to create exact replicas for training electronic warfare operators. The Soviet approach differed from that of the Western Allies. While the British and Americans could afford to create special units for technology hunting, the USSR operated under the most severe struggle for survival. Each operation to capture German equipment was planned with an emphasis on minimizing risks and maximizing effectiveness. Soviet intelligence officers preferred to operate in small groups, carefully choosing targets and moments for attack. Relations between the Allies regarding the exchange of radar technologies were complex and ambiguous. On the one hand, there were official channels for information exchange. The British provided Soviet representatives with data on German radars, including some results of studying captured trophies. On the other hand, each country sought to maintain a technological advantage, concealing the most important details. Colonel Ivan Petrov, who headed the Soviet technical mission in Great Britain, recalled, "Our British colleagues were polite and helpful. They showed us their radars, explained the principles of operation, but when it came to specific circuit solutions or production technologies, the conversation invariably shifted to another topic." The Americans were even more cautious in exchanging technologies with the USSR. Despite the official policy of cooperation under the Lend-Lease program, supplies of radar equipment were limited to outdated models. The latest developments, especially in the field of microwave technology, remained classified as top secret, even for the Allies. This restraint in technological exchange pushed each country to independent actions to capture German equipment. Soviet, British, and American intelligence officers sometimes found themselves rivals, hunting for the same objects. There is a known case when, in April 1944, Soviet and American groups simultaneously tried to capture a radar station in East Prussia, and only chance prevented a clash between the Allies. Despite the competition, the combined efforts of the Allies in the radar war bore fruit. By the end of 1944, the German air defense system was virtually paralyzed. The Luftwaffe lost its once undisputed air superiority. The radars, which were supposed to be the shield of the Third Reich, proved powerless against the combined methods of electronic warfare developed based on captured technologies. The technological legacy of the Würzburg extends far beyond the war years, becoming the foundation for the development of modern air defense systems. The captured German radar, seized by Soviet intelligence during the height of the war, proved to be not just a temporary advantage, but a true window into the future of radar technologies. It laid down principles that are still used today in Russia's most advanced air defense complexes. After the end of the Great Patriotic War, Soviet designers continued to develop technologies acquired through the study of the Quote. In 1947, the Quote-2 radar station was created, which already significantly surpassed the German prototype in detection range and accuracy. It was the first to implement an automatic target tracking system, conceptually based on German developments, but significantly improved by Soviet engineers. The next important step was the creation of the S-25 Quote-3 anti-aircraft missile system in the 50s. Its radar system used a phased array antenna, a technology whose rudiments were already visible in experimental models of the Quote-4. This complex for the first time allowed effective combat against high-altitude reconnaissance aircraft, which were previously considered invulnerable. Quote recalled academician Alexander Raspletin, chief designer of the first Soviet anti-aircraft missile systems. Quote, in the 60s, the S-75 system appeared, which could simultaneously track multiple targets and guide missiles to them. This principle of multi-channeling was conceptually envisioned in later modifications of the Quote but fully implemented only by Soviet designers. The S-75 became the world's first complex capable of effectively combating ballistic missiles. A true breakthrough was the creation of the S-300 system in the 70s, which is still considered one of the most effective in the world. It implemented the principles of digital signal processing and adaptive interference filtering, technologies conceptually linked to solutions first studied on the captured Würzburg. Modern Russian S-400 and S-500 systems represent the pinnacle of evolution, whose beginning was laid by the study of the German radar. They retain some basic principles: the use of phased array antennas, multi-channeling, adaptive interference filtering, but implemented at a completely new technological level. An especially important legacy of the Würzburg was the concept of an integrated air defense system, where various detection and engagement means work as a single organism. This principle, first implemented by the Germans in the Himmelbett system, was developed in Soviet and Russian complexes to the level of fully automated control systems. The technological relay race, which began with the daring operation to capture the German radar, continues today. Modern Russian air defense systems, recognized as among the best in the world, carry in their genetic code engineering solutions first seen by Soviet specialists when studying the captured Würzburg.